Recent studies have reignited interest in the role of orbital variations, specifically precession, obliquity, and eccentricity, in Earth's climate system. Two groundbreaking papers published in Science and the International Journal of Digital Earth provide new insights into this long-debated issue. In particular, the work by Barker et al. 2025 underscores the distinct roles of precession, obliquity, and eccentricity in the Pleistocene's 100 glacial cycles, while Cow et al. 2005 expand upon this investigation by exploring how planetary orbital variations influenced Earth's modern temperature. They calculated the impact of changes in the orbits of different planets, Earth's rotation, Earth's revolution, the Moon's orbit, and the orbits of other planets on Earth's temperature variations. These studies provide a comprehensive update to our understanding of how orbital mechanics have shaped past and future climate variability. Planets follow stable cyclical orbits, influencing and shaping various components of Earth, particularly seasonal climate and plant changes, which are mainly driven by Earth's orbit around the Sun. However, people often fail to connect these changes with celestial influences. For example, herbaceous plants complete their life cycle each year, while woody plants add one tree ring annually, and the variation in tree rings reflects the impact of Earth's revolution. The planets in the solar system move rapidly alongside the Sun, interacting with each other while maintaining balance. As Earth moves, its components also adapt to changes in its orbit. Yet people rarely associate internal changes on Earth with variations in celestial orbits. In this study, we demonstrate the influence of changes in planetary orbits on Earth's atmospheric water vapor through variations in Earth's atmospheric water vapor. As shown in the figure, on a daily scale, Earth's rotation dominates atmospheric water vapor variations. Earth completes a 24-hour rotation cycle, while the Moon's orbit about 27.3 days, Earth's orbit about 365 days, and other planetary orbital changes are relatively minor on this timescale. Variations in land-sea distribution cause differences in solar radiation intensity across regions, shaping diurnal climate patterns and associated water vapor fluctuations. Analysis shows that water vapor variation curves for consecutive days are highly similar, with minimal amplitude changes, reflecting the consistent periodicity of Earth's rotation and its stable regulation of daily water vapor. On a monthly scale, Earth's rotation completes one cycle daily. The Moon's orbit completes about 1/27.3 of a cycle. Earth's orbit advances only 1/365th of a cycle, and other planetary orbital changes remain minor. Daily water vapor fluctuations caused by Earth's rotation are minimal, making the Moon's orbit the dominant driver of atmospheric water vapor variations. The Moon's gravitational effects on tides and atmospheric circulation became evident at this scale, with its periodic changes shaping intramonthly water vapor distribution patterns, though modulated by Earth's orbital baseline, leading to inconsistent monthly patterns. On an annual scale, Earth's rotation completes one cycle daily. The Moon's orbit completes one cycle monthly. Earth's orbit advances about 1/13th of a cycle per month, and other planetary orbital changes are relatively minor. Earth's rotation and the Moon's orbit, completing multiple full cycles within a year, have stabilized effects. Thus, Earth's orbit becomes the dominant driver of annual water vapor fluctuations. Its elliptical orbital motion determines seasonal variations in solar radiation, directly shaping global water vapor distribution and circulation, and forming distinct seasonal climate patterns. On an interannual scale, Earth's rotation, the Moon's orbit, and Earth's orbit exhibit similar periodic repetitions. Their combined effects set the baseline for water vapor variations. However, Differences in other planetary orbital positions emerge at this scale. Some planets complete full cycles, while others complete only partial cycles. These differences disrupt the complete repeatability of interannual water vapor changes, causing variations in water vapor distribution at the same time each year. Notably, the Moon's non-integer orbital period, about 27.3 days, combined with asynchronous changes in other planetary orbits, it makes interannual water vapor fluctuations highly dependent on the collective orbital states of all planets. This explains the variability of weather patterns, which rarely repeat exactly. Through above analysis and physical reasoning, as shown in the figure, we have concluded that water vapor changes at different timescales are primarily driven by the orbits of planets at different hierarchical levels. Daily scales are dominated by Earth's rotation, monthly scales by the Moon's orbit, annual scales by Earth's orbit, and interannual scales by the combined effects of other planetary orbits. From a spatio-temporal perspective, hourly water vapor changes are snapshots of the 24-hour cycle. Daily changes form points on the monthly scale. Monthly changes reflect stages of Earth's orbit, and annual changes are units of the interannual scale. Small fluctuations in higher-level orbits often trigger significant changes at lower levels, creating a top-down driving effect. Finally, attached is the prior work of the research group related to this study. The group has over a decade of research experience in this field and has explored the impact of planetary orbital variations on Earth's climate from the perspective of changes in planetary orbits. Thank you for your attention.